Hi everyone, we are from Group 3 and we would like to present about the analysis of 3-mercaptol-hexanol in white wine sample. Here is our team members. I'm Ng Ziyan and our group leader is Wong Zihao. Our other team members are Wong Ke-ying, Wong Ziying and Tam Sim Ying. White wine is chosen as the sample for this scenario due to its complexity in terms of both inorganic and organic constituent. White wine contains a variety of chemical compounds including water, sugars, acid, alcohol, aroma compounds such as 3-mercaptol-hexanol, and the potential for inorganic contaminants like arsenic. Analyzing white wine presents a real-world scenario relevant to the beverage industry, where quality control is critical for ensuring product safety, meeting regulatory standards, and maintaining the desired sensory characteristic. The aroma of white wine is one of the quality assessments should be monitored in order to ensure each batch of the white wine aroma is consistent. We have chosen 3-mercaptol-hexanol as our analytes. It is an organic sulfur compound which has significant impact on several foods and beverage. It is also formed during alcoholic fermentation from an odorless precursor present in grapes that contribute to the fruity aromas in wine. It has a chemical formula of C6H14OS and a boiling point at 198 degrees Celsius. It is also in liquid state and polar due to a H group. For this organic analyte, we suggest liquid-liquid extraction for the sample preparation. This is because it is highly soluble in organic solvent, which can make the extraction process to be easier. Now we come to sample preparation, where liquid-liquid extraction is used. First, 500 ml wine was placed in an aluminium flask and cooled to 1 degree Celsius in an ice bath under nitrogen. It is spiked with 50 microliter of 3-mercaptol-hexanol solution in pentane as internal standards. After equilibration for 5 minutes under stirring, 100 ml of dichloromethane were added and the mixture was stirred for 15 minutes at 700 rpm. Then the mixture was supplemented with 100 ml of dichloromethane and further stirred for 50 minutes. Next, the organic phase was separated in a separatory funnel, centrifuged for 5 minutes. It is dried over sodium sulfate and concentrated under vacuum at 25 degrees Celsius to about 2 ml. 500 microliter of Efigel 501 were loaded in a pasture pipe, and it is conditioned with 5 ml of isopropyl alcohol and 5 ml of pentane dichloromethane at a ratio of 2 to 1. Then, the wine extract that diluted in 2 ml of pentane was passed through the column, which was then washed with 25 ml of pentane dichloromethane. The thiols were finally eluted with 5 ml of pentane dichloromethane. The extract was washed with 1 ml of millipore water, dried over sodium sulfate and concentrated to 500 microliter by distillation at 35 degrees Celsius and partial rectification using a Dutton column. Then the extract was further concentrated down to 100 microliter under a nitrogen flow and ready to be analyzed.
The first step is to analyze the mass data scanned at each maximum GC Negative field is used. The accepting voltage and negative field are continually adjusted to control the ion velocity and trajectory. The mass return is plotted on a linearity equivalence scale to show as histogram of the amount of ion that reach the detector based on their mass to charge ratio at the second step. Lastly, analyze the intensity of certain mass in relation to time. The mass ratio intensity of normal mass pattern map out 2 or 3 dimensions, and the GC retention period over which the mass data are obtained map out the third dimensions. The spinel injection is suitable for our analyte with low concentration of gas compound because it is important to add as much as we can to improve the sensitivity. The carrier gas in the GC for 3-mercaptol-hexanol is helium at flow rate of 1/2 ml per minute. The open Boolean column is used because it is high quality and easy operation. For the oven, the temperature program is 35 degrees Celsius for 5 minutes, 1 degree Celsius per minute to 40 degrees Celsius, and then 10 degrees Celsius per minute to 250 degrees Celsius. In interface, we use jet separator to allow low mass carrier gas molecule diffuse from jet acid and leaving the heavier analyte molecules. In chemical ionization, some of the sample molecules are ionized through photon transfer, electron transfer, and adult formation when they collide with the free ionized reagent gas. In double frequency mass analysis, the ions beam flow through the area of electric field because the particles exiting the ionization chamber do not all travel at the same speed. For the detector, we use fan ionization detector because it is suitable for our analyte, which is organic compound. A signal is produced when the quantity of ion passed through the detector is measured.
As for the procedure in handling GCMS, first of all, calibrate the instrument using a standard wine mixture containing known concentration of 3-mercaptol-hexanol, followed by a small volume of the concentration sample is injected into the system. Thermal desorption follows for 5 minutes in the injector with spitless mode at 250 degrees Celsius as well. Then the compounds in the sample are separated using GC and utilize a suitable capillary column for the separation of volatile compounds. The eluted compounds from GC column enter the MS for identification. Thereby, the MS is set to scan with single ion mode for the characteristic ions of 3-methylhexanol. Last but not least, the enhanced Chem Station software and Statistica V10 software are used to analyze the samples to identify and quantify the presence of 3-methylhexanol in the sample. There are a few advantages in GCMS since it is highly sensitive and can detect trace amount of compounds, making it suitable for analyzing the low concentration of 3-methylhexanol in white wine. Next, it also provides selective identification of compounds based on their mass to charge ratio, allowing for the specific identification of the analyte among other wide components. Other than that, the quantitative analysis of GCMS has enables the determination of the concentration of the analyte as well. It also separates the different compounds in a sample, allowing for the resolution of complex mixture present in the white wine. Next, we'll move on to the limitation of GCMS. First of all, 3-methylhexanol requires derivatization before the analysis to enhance volatility or stability. This additional step can increase the complexity and time of the analysis, whereby the complex metrics of white wine can cause interference, affecting the accuracy and precision of the analysis. Sample preparation and cleanup steps may be necessary to mitigate matrix effects. Moreover, GCMS is the most suitable for the analysis of volatile and semi-volatile compounds. Non-volatile or high molecular weight compounds may not be well suited for this technique. GCMS instruments are also relatively expensive to acquire and maintain, which can be a limitation for smaller laboratories or research facilities.
The first protocol for analysis, we use calibration method. We need to prepare for the stock solution, and for the preparation, we need material and reagent, which is 3-methylhexanol, solvent, volumetric flask, pipettes, analytical balance, and graduated cylinders. We need to weigh a known amount of 3-methylhexanol using an analytical balance and dissolve the weak compound in a suitable solvent to prepare a stock solution. Next is the determination of 3-methylhexanol using calibration method. We need to prepare a series of dilutions with known concentrations by using the stock solution that we prepared earlier. Then, set up the GCMS instrument with appropriate conditions, including injection volume, column temperature program, and mass spectrometer conditions. We need to inject each standard solution into the GCMS instrument under the same conditions that will be used for the sample analysis. Lastly, we need to record the instrument response, which is peak area or event height for each concentration, and a calibration curve will be constructed by plotting the peak area or height against the known concentrations of 3-methylhexanol.
Our next protocol for analysis of the concentration of 3-methylhexanol in white wine is by using AOSC official method 985.01. For first is prepare a series of calibration standards with known concentration of 3-methylhexanol in a suitable solvent. The concentration range should cover expected levels in white wine. And the second is to optimize the chromatographic conditions for the separation and detection of 3-methylhexanol. The third is inject the prepared standards and sample into GCMS system. Ensure that injection volumes are consistent. And our fourth is employ a non-polar column for separation to enhance resolution of volatile compounds. Adjust the temperature gradient for optimal separation. The fourth is the use electron impact ionization for mass spectroscopy detection of 3-methylhexanol. Monitor a characteristic mass to charge ratio for identification. And now next is quantify the concentration of 3-methylhexanol by comparing peak area or height of the samples to the calibration curve. Next, implement quality control measures including the analysis of blanks and spike sample to ensure the accuracy and precision of the results. Next is reporting. Report the concentration of 3-methylhexanol in specified units. Next, ensure that all steps of the analysis are well documented, including instrument parameters, calibration data, and any deviation from standard method. Here has shown the result that how the 3-methylhexanol concentration in white wine should be analyzed. The peak area between those phenolic compounds should be analyzed in according to the peak area.